Hello, my name is Dmitry Vyukov. I work as software engineer at Google. A little bit about me, I did a bunch of work on Go. I did the current scalable Go-routine scheduler, integrated network poller, parallel GC, concurrent sweeping, a bunch of memory allocator improvements. I wrote current implementation of most of the synchronization primitives in Runtime and standard and sync package. I did the race detector, the blocking profile, and some compiler optimizations and more. In total, 800 commits and filed more than 500 bugs. But actually, I'm not on the Go team. I'm on the dynamic testing tools team where I work on our flagman products called thread sanitizer, memory sanitizer, and address sanitizer, which find all kinds of nasty bugs in C++ programs. And now they are part of both GC and Clang compilers. So I'm going to talk about 3 dynamic tools that I created for Go. First is a data race detector. Second is GoFuzz, which is a randomized testing system. And then very briefly about execution tracer, which will be available in 1.5. So the data race detector. If you write Go code, you most likely don't have a choice to not write concurrent code. And with concurrent code came data races, and data races are bad. So what is a data race? Data race occurs when 2 Go routines access the same variable concurrently, and at least one of the accesses is a write. And if you have a data race, all bets are off. Any data race can compromise correctness, stability, and security of your program. So if you insert concurrently into hash map, that's obviously bad. Hash map can be corrupted. But even if you just increment a stat counter concurrently, that also can corrupt memory. Why? Because compilers assume that your program is race-free and do aggressive optimizations based on that assumption. For example, if a Go routine writes to a variable, compiler can assume that this Go routine owns this variable at this point in time, and, for example, use it as a scratch storage for something else. So if there is a concurrent read, it will read completely unrelated value. If there is a concurrent write, it will corrupt some unrelated value. And data races are also non-deterministic and very hard to debug. They usually happen only in production, like once in a while. But fortunately, Go comes with a built-in data race detector, which is very simple to use. You just need to add -race flag when you build, test, or install your packages, and that's it. For example, if you have this simple program that inserts into hash map concurrently, and you run it with a -race flag, it will print the following data race report. The report contains stack traces for both of the race and memory accesses, and also says which Go routines do those accesses, and says whether it's a read or a write. And then it contains stack traces where the involved Go routine were created. And this information is usually enough to pinpoint bug in your code. So when I implemented the race detector, the first obvious target was the standard library itself. I've set up continuous testing, and today that has found more than 70 bugs in standard library. Some of them were kind of test only, but lots of them were actual harmful bugs in production code. We also have continuous testing for all of our Go code in Google. And today, I filed 350 bugs for those projects, and there is also probably more found by other people. And there is also an unknown amount of bugs in the wild that I don't know about. A little bit about how does this magic work inside. There are 2 parts. The first part is compiler instrumentation module, which intercepts all memory accesses and function entry and exit, and inserts calls into runtime library before those events. And the second part is the runtime module, which handles memory accesses to catch the race accesses. It also handles all of the synchronization to understand what memory accesses synchronize with each other and not produce false reports. It handles function calls to collect stack traces for reporting, and also goroutine creation and exit to keep track of live goroutines. The algorithm is based on direct dynamic modeling of the happens before relation that you can find in the Go memory model. And what it means in practice is that false positives are impossible. So any report is a real bug. But unfortunately, false negatives are possible sometimes. Some usage tips. This is a dynamic tool, so it's only as good as your tests are. If your tests don't create any goroutines, then there is no chance that you will find data races. So do write good concurrent tests. If a component can be used concurrently, then write a test where it is actually used concurrently. You don't need to check for anything special in this test. You just need the concurrency for the race detector to catch races there. But unit tests still usually not good enough for concurrent testing, so it makes sense to run the whole binary race enabled on the real workload. For example, you can run your integration test with the race enabled, or you can run even binaries in production as canary or in staging, or mirror a part of a real traffic to a race binary. Yeah, and also it's useful to set up continuous testing because of the possible false negatives, that is missed reports. But any data race is caught eventually, so if you run it continuously, you will catch all data races in the code. So that's it for the race detector. And now I move to GoFast, which is a randomized testing system. You hopefully have unit tests for your code, and maybe even system and integration tests, and maybe even stress tests. But I want to talk about a completely different approach to testing, which can potentially find lots of bugs that other approaches don't find. And the good news is that you will not actually need to write any tests. So this approach is randomized testing, and it's intended mostly for programs that parse and process complex inputs. The high-level idea is quite simple. We just generate a random blob of data and feed it into a program and see if it crashes. If it crashes, we've got profit. And there are two advantages of this approach. The first is it's very cheap to use. You don't need to write any actual tests. And the second benefit is that it doesn't have any bias, so it won't miss bugs in the code because it has some misplaced trust into a piece of code. But completely random blobs like white noise won't find lots of bugs because the code will just bail out early on some check, and you don't actually check the rest of the code. So the question here is, how can we generate diverse but meaningful inputs that will actually trigger nil derefs and off by ones in our code? One of the known answers to this question is so-called coverage-guided fuzzing. It is a form of a genetic algorithm which works as follows. We first instrument the program for code coverage. It's the same code coverage that you see with go-to-cover. It allows us to understand what lines of code were executed. Then we collect some initial corpus of inputs for the program. And it can be just inputs that you use in your unit tests. Then we choose one input randomly from this corpus and slightly mutate it. For example, flip a bit or replace a byte with a random byte or remove a byte. And then we execute this input and collect coverage. And if this input gives us new coverage, that is, it triggers execution of some lines of code that are not executed on any of the existing inputs, that then we add this input back to the corpus. And this last part is repeated. So let's consider a simple example. We have this program that wants input A, B, C, D to crash. And we start with the corpus containing just single input, which is an empty string. We start mutating this string, and it won't take long until we get this string containing letter A. And at this point, we say, aha, this input triggered execution of a line of code that wasn't executed previously, so we add this input back to the corpus. So now we have two inputs. One is empty string, and one is A. We continue mutating those inputs, and soon we get string AB added back to the corpus, and soon we finally get A, B, C, D, and crash the program. So the key point here is that the fuzzer doesn't need to guess the whole input at once, which is quite difficult problem. It does this incrementally, basically guessing the right input for the crash byte by byte, and this is much simpler problem. This approach is used in a number of existing tools, mainly for C and C++, mainly for security testing. But GoFuzz contains a secret sauce consisting of two ingredients. And let's consider this piece of code. This is a real code from the image PNG reader, and it does checksum verification. If the checksum in the file is not correct, then we bail out and don't execute the rest, don't do anything with the image. And the probability that random mutations will alter the image itself in an interesting way and also guess the checksum, which is 4 bytes, and also update it in the right position in the input is basically 0. So it won't happen, so this is kind of a game over for fuzzer. And the first secret ingredient, I call it sonar, and it allows to resolve this problem. The insight was that we don't actually need to guess the correct value of the checksum because the program already knows it. So we just need to fetch it from the program itself. We already did code instrumentation for coverage. So here we do a different kind of source code instrumentation. We find all comparison operations in the code, and then intercept the operands of the comparison operation and pass them into runtime. So in this case, we will have the checksum from the file, and let's call it value 1, and the checksum, the correct value of the checksum computed from the input. Let's call it value 2. And then what the runtime library does, it searches for the value 1 in the input, and if it finds those bytes in the input, it just replaces them with the value 2. And like bingo, we've got the new image with the correct checksum in basically no time. And the second secret ingredient, about the second ingredient. So the mutation and sonar only do kind of a low-level mutations of the input. They do so-called bit flipping. If you have an XML input, they can, for example, replace a slash with an opening bracket. And that can find some bugs in the parser. But what we do for XML input, we actually want higher-level changes and mutation of this input. We want for example, insert new elements, add and remove attributes, and so on. And the second secret ingredient is called Versifier. And what it does, it tries to reverse engineer the protocol contained in the input and learn its structure. For example, if it sees a sequence of digits, it guesses that this is probably a number in the input. If it sees something in quotes, it assumes that this is like something in quotes in the input. If it says something, comma, something, comma, something, it assumes that this is probably a comma delimited list in the input, and so on for brackets and key value pairs, and also for new lines, because new lines usually serve some structuring purpose. So for example, it can understand that this is a line of code. It contains a comma delimited list and of key value pairs, and this value is a quoted string, and this value is a number. And after that, it does structural mutations with this knowledge. So here you can see a set of real outputs of Versifier for the given XML. And I've checked that those are actually all valid XML, so they will pass through the parser and reach the rest of the program. And you can see all kinds of weird things here. So for example, in the first input, it inserted a nested item element and then duplicated the property element here. Here it inserted a new attribute and so on, and inserted some weird numbers and changed the identifiers. But Sonar and Versifier not just generate interesting inputs, they also amplify efficiency of the random mutations because they are included into the same closed coverage guided loop. So here you can see the overall structure of the Go fuzz operation. We start with the corpus here, choose a random input, then either mutate it or versify, and then execute and collect coverage. If the test crashes, then great, we've got a new crasher and we store it into a file. If there is no new coverage, then we usually just discard this input. But sometimes we pass it to Sonar to, for example, update the checksum in the input or something and execute it again. If there is a new coverage, then we first minimize this input to a minimal form that gives us the same new coverage. Then we smash it. And smashing is a mandatory attention to every new input in the corpus. During smashing, we try to flip every bit one by one, then flip every byte one by one, then replace every byte, 2 bytes and 4 bytes with a set of special values like 0 or -1. Then we try to trim the input after every byte and so on. Then we also pass it to Sonar. For example, if this input uncovered a piece of code with a switch statement, and only one case was executed in this particular execution, Sonar can potentially instantly generate inputs that will cover all, that will execute all other cases in this switch. Then we add this input back to the corpus, and this continues infinitely in parallel. Okay, now you may wonder, this is so complex and complex. Did it actually find any bugs? And yes, it did. Over the last several months, I've applied to standard libraries and some other packages, and I found 115 bugs in the standard library. 66 of them are now fixed, and this is probably the most well-tested Go code out there that was there for like at least several years. Also 43 bugs in the golang.org/x packages, and 134 bugs in other packages. Some of them were actually found by external people by just applying GoFast to their packages. And here you can see some real examples of the bugs that I found. For example, regarding the bias, I didn't want to write tests for formed package for a long time because I thought that this will be a wasted effort because the formed package doesn't contain bugs, right? But it turned out that there is at least 7 crashers in the Go formed package. And here is one. If you try to format this particular string, it will crash with index out of range. And if you try to compile this particular string as a regex, it will also crash. And if you try to deflate that particular 10 bytes it will just run forever, consuming CPU. And the FLATE is one of the compression algorithms in HTTP, so you can make the conclusions. If you try to compile this particular line of code, which is perfectly legal, it will crash the compiler. And there were all kinds of panics, instant program terminations, stack overflows, excessive user-controllable memory consumption, and a whole bunch of logical bugs as well. So if you have something that can be potentially tested with GoFuzz, I suggest you to use it. And it's quite simple. You go get GoFuzz, then write a test, which is just a function that accepts a byte slice, and then do something with this byte slice. For example, try to deserialize it, or decompress, or something, or parse. Then you build it with a special GoFuzz build provided utility, which does the code coverage instrumentation and sonar instrumentation. Then collect some corpus of inputs, and then run it. And it will run and collect crashing inputs in files. So that's it for the GoFuzz. And the last part is a brief announcement of the execution tracer, which will be a part of 1.5 release. And it gives you insight of the dynamic execution of your program. So what it does is it captures with basically nanosecond precision a set of events during execution. Events like coroutine creation, start, end, blocking, unblocking on synchronization primitives, also network blocking, system calls, and GC events, and some other events. And then it allows to visualize this in the following form. So each row is a processor or a worker thread, and then slices is coroutines, and arrows mean either coroutine creation or unblocking on synchronization primitives. And most of the events also has full stack traces, so it's quite easy to figure out what's happening. It allows us to understand contention issues or bad parallelization issues and so on. So to recap, the race detector is an essential tool for any concurrent code that is for all of the Go code. So use it. GoFuzz is for parsing of complex inputs. Try it. And the execution tracer is deep dive into execution, and it will be available in 1.5. But if you want to try it now, it's already on TIP, so you can check out TIP and try it there. Thank you. I'm ready to take any questions.